Hello, my friends. So this time we're going to be looking at something called related rates. Now, previously, we had talked about implicit differentiation. Implicit differentiation, just to start off, is when we had some function that was in terms of both x and y, but we couldn't really separate the x and y. So when we did that, we took the derivative with respect to x, and we always had to have a dy dt term there. So in this quick example, I've got dvx of x squared plus x, y squared equals 6. That's going to give us 2x plus, remembering the product rule, derivative of x is 1 times y squared plus derivative of y squared. We've got x multiplied by 2y times, dy dx equals 0. With implicit differentiation, we had that dy dx because y is treated as a function of x. We do not have a dx, well, because that would just be 1. The rate of change of x with respect to the rate of change of x. It's in terms of itself, so it would just be 1. But what happens if we change the variable and say make it with respect to time? What that's saying then is that we've got this function x, which is actually some function of time. So like our horizontal position depends upon the time that we have. And here we've got our horizontal position combined with our vertical position is really some function of time. So all of a sudden, x is a function of some other variable, y is a function of some other variable, this related third variable time. What we're going to be doing is looking at this idea of related rates. So here's our situation. Air is being pumped into a spherical balloon. So we start blowing up the balloon, and the balloon starts getting larger and larger and larger. Well, the radius is going to be increasing, the surface area is going to be increasing, the volume is going to be increasing. So if we have a balloon with a volume increasing at a rate of 100 cubic centimeters per second, so that's the volume, the air that's going in. You can try to envision this. The balloon is getting larger, but that's also causing the radius to change. So the volume is a function of time. We've got the radius of this balloon is a function of time. We can compare those separately. Perhaps in previous experiences you talked about parametric equations where x is a function of time and y is a function of time. Same idea. So here's the question statement. How fast is the radius of the balloon increasing when the diameter is at 50 centimeters? I'm going to change this word because I made a mistake later on. I'm just going to say when the radius is 50 centimeters. So we can imagine what's going on there. Air is going into the balloon expands, volume is changing, the radius is changing. The statement up in the top right, the volume is increasing. Well, that is the rate of change of the volume with respect to time. dv dt, rate of change of volume with respect to the change in time. Like dv dt, change in volume, is 100 cubic centimeters per second. So let's go through and find out, because in the end, how fast is the radius of the balloon increasing when the radius is 50 centimeters? We're trying to find out what's the rate of change of the radius with respect to time. So what do we know? We've got the volume is 4/3 pi r cubed. That's the formula for the volume of the sphere. We're given dv dt is 100 cubic centimeters per second, and that the radius is 50 centimeters. I'm going to start off, and what are we finding? Once again, dr dt. That's our end goal. So we're given this volume formula, 4/3 pi r cubed. We could find the volume when the radius is 50, but that's not what we're interested in. What I'm going to do here is I'm going to take the derivative with respect to time. That's going to give me dv dt, so the rate of change of this statement with respect to time, the rate of change of volume with respect to time. Here, I'm going to use the power rule. Remember that 4/3 is a constant, pi is a constant, r is some function of time. So power rule, I'm going to multiply. I'm going to get 4 pi r squared, but because r, the radius, is a function of time, that's going to be dr dt, which, that's what we're trying to find. We know that volume is, or excuse me, the change in volume is 100 cubic centimeters per second. We've got 4 pi r squared, so that's 50 centimeters squared times dr dt. Now it becomes straightforward algebra, just arithmetic manipulation to solve for dr dt. That's going to give us dr dt. We're going to have 100 cubic centimeters per second. We're going to divide that by 4 pi 50 centimeters squared. Put that square on the outside there. Look at the units. See what happens. We've got centimeters cubed divided by centimeters squared. That's going to leave us with centimeters per second, which makes sense for the change in radius compared to the change in time. So what happened here is that we've got these related rates. We are comparing the rate of change of the volume to the rate of change of the radius with respect to time. We're taking the derivative with respect to time. Let's try another one. Ladder 10 feet long rests along a vertical wall. So you can see there, we've got our ladder 10 feet long. Bottom of the ladder slides away from the wall 10 feet per second. So that X, it's sliding away 1 foot per second. As a result, Y is going to be starting to fall. The height is decreasing there. How fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? So we are given dx dt. It's 1 foot per second. So horizontally, that X is increasing by 1 foot per second. We want to find dy dt. So I need to look at the situation and what's going to connect everything there. Well, that's a wall, that's a ladder, that's a right triangle. So we know that we have x squared plus y squared equals 10 squared. I'm going to take the derivative with respect to time. So d dt. How is the x changing over time? Well, that's going to give us 2x times dx dt. Plus, derivative of y squared with respect to time is going to be 2y times dy dt. And derivative of 100, or 10 squared, is 0. I see that x and y are both multiplied by 2. I'm going to solve this for our goal, dy dt. So I've got dy dt is equal to negative x over y times dx dt. So we have the rate of change is proportional to the length of those sides. Now we know that when x is 6, that's what we're trying to find, how the ladder is changing at that time. Well, that's 6, and the hypotenuse is 10. That missing side, the height at that moment, at that very instance, is 8 feet. So we've got dy dt is equal to negative 6 over 8 multiplied by 1 foot per second. So we have negative 3/4 feet per second is the rate at which the height is falling. And it's negative. It makes sense because it's falling down. It's dropping down the wall. What happened? So I had a diagram relating different variables. I started off, I've got something that connects different variables. I know what I'm looking for, and then I'm going to take the derivative with respect to time. From there, it's a lot of algebraic manipulation. Let's try another one. Water tank has the shape of an inverted circular cone with base radius 2 meters and height 4 meters. So there's our 2 meters, there's our 4 meters. Water is being pumped into the tank at a rate of 2 cubic meters per minute. We've got dV dt is 2 cubic meters per minute. Find the rate at which the water level is rising when the water is 3 meters deep. So that's telling me when my height is 3, rate at which the water level is rising. It's asking what is dH dt. Now, because I remember all of my formulas, I know that the volume of a right cylindrical cone is pi thirds r squared h. Ooh, uh-oh. We've got two variables there. We could use the product rule, or I can recognize that we have a set of similar triangles here. And so in our similar triangles here, we've got that 2 is to r as 4 is to h, or the height is always double the radius. What that gives us, now since we want dH dt in the end, I'm going to solve this and say r is equal to 1/2 h. And now let's start differentiating. If I take take a step back. Let's make that substitution. Get everything in terms of one variable. That way I do not need the product rule at that moment. So I'm going to make that sub. Volume is now pi over 3 h over 2 times h, so that's squared. So the volume is pi over 3 h cubed over 4. So we get the volume is pi over 12 h cubed. Now I'm going to take dVt, take the derivative of this statement with respect to time. That's going to get us dV dt, rate of change of volume with respect to time. And then we're going to have pi over 4 h squared times dH dt. We know h is 3. We can make that substitution. We know dV dt is 2. Some basic, straightforward algebraic manipulation can solve for dH dt. So we're looking at related rates here. In this sense, we had the volume of a cone. Volume of a cone is in terms of both the radius and the height. Needed something that connected the radius and the height, and that goes back to a similar triangle there. I made the substitution at the start, and then differentiated, but you can differentiate first and then later make the substitution. Take a look. We've got some different problem solving strategies. Read carefully. What do you know? What are you trying to find? It helps to draw a picture. Draw a picture. It helps to draw a little kitty cat. Draw a little kitty cat. But what's your notation? Be careful with that. look for the derivatives. We're looking at rates. We're going to have d dt, the rate of change of something with respect to time. Let's take another one. Car is traveling west at 50 miles per hour, and car B is traveling north at 60 miles per hour. Both are headed for the intersection of the two roads. What rate are the cars approaching each other when car A is 0.3 miles and car B is 0.4 miles from the intersection? So here's the idea. We've got some intersection. A is traveling west. So west is that direction. B is traveling north, which implies then that B is somewhere down here. A is somewhere over on the right. That way, we're approaching towards the intersection. Now, in the end, it's asking us at what rate are the cars approaching each other. That's going to be the distance between. So I'm going to put that in there. That's D. D for distance. Now, since I'm looking at east-west, north-south, I've got a right triangle. I remember my handy distance formula. It's going to be change in x squared plus change in y squared. So the distance, the location of x, the location of y, I'm going to do it relative to the origin 0, 0. Car A starts at 0.3 miles, and that distance is decreasing at 50 miles per hour. Car B, is starting at, I'm going to say, car B is starting at negative 0.4, because relative to 0, 0, I am south. So negative 0.4 plus 60 miles per hour. Now, thinking about that, I'm going to say my distance is going to be 0.3 minus 50t. So the distance, our location, is in terms of time. So I can say d squared is 0.3 minus 50t squared, plus we have 60t minus 0.4 squared. We can take the derivative of this now. So I could multiply all that out. I'm just going to end up using the chain rule. So I'm going to take the derivative of this with respect to t. That's going to give us 2d times dt dt. We're going to have equals, we have 2.3 minus 50t multiplied by negative 50. Because the derivative of negative 50t is negative 50. I do not have dt dt. That would just be 1. Plus, we've got 260t minus 0.4 multiplied by 60. I'm going to neaten some things up. I noticed 2 holes in there. We've got d times dt dt equals negative 50.3 minus 50t plus 60 multiplied by, where am I going, 60t minus 0.4. So at that time, let's figure out the pieces that we have. We know that at the time when we are 0.3 and 0.4 distance away, 0.3 miles and 0.4 miles away, that's basically at time 0. So we want to find dt dt at, say that a lot of times fast, at time equals 0, because that is when time is 0, we are 0.3 and 0.4 miles away from the intersection. We notice that we also need the value of d. Since we've got 0.3 and 0.4, Pythagorean theorem, d is going to be half mile, 0.5. Plug everything in. So we got 0.5 times dt dt equals negative 50 times 0.3 plus 60 multiplied by negative 0.4. And then you can solve dt dt as you wish. Notice it's going to be negative. Why is it going to be negative? Think back to the example. Make it make sense. Let's do another one. Someone's walking along a straight path at a speed of 4 feet per second. Ooh, that's dx dt. 4 feet per second. Searchlight located on the ground 20 feet away from the path. It's kept focused on that person. So as that person walks over, that's going to be rotating. At what rate is the searchlight rotating when the person is 15 feet away? So that's when we've got x equals 15 feet from the path, from the point on the path closest to the searchlight. So x is going to be 15 feet. I need something that's going to connect all three of those variables. I see I've got a right triangle. I've got an angle. Relative to that angle, we have opposite side, and we have adjacent side. At what rate is the searchlight rotating? That's going to be d theta dt. What is the change of the angle measure, in radians, of course, with respect to time? So I need something that's going to connect in with the angle. Well, I've got the opposite side. I've got the adjacent side. That's tangent. I can go on and say Tangent of theta is equal to x over 20. I can differentiate that. So I'm going to take the derivative with respect to time, knowing that that's going to give us our dx dt, and it's going to give us our d theta dt. Here on the left, I've got secant squared theta multiplied by d theta dt, chain rule, equals 1 over 20 times dx dt. Ooh, x just disappeared there. X worked itself out. I don't care our distance away. Or do I? So I'm going to solve d theta dt. It's going to be 1 over 20 dx dt is 4 feet per second multiplied by cosine squared of that angle. So, do we need to know the angle? Actually, no. This is 20. This is 15 at that time. I notice this is 4 times 5. This is 3 times 5. Our Pythagorean triple. At that moment, this side is going to be 25 feet. That's useful because I know cosine of some angle is going to be the ratio of the adjacent to the hypotenuse is 20 over 25 is 4 over 5. Therefore, theta dt is 1/5 multiplied by 4/5 squared. We've got the theta dt. It's going to be 16 over 125, and that is radians per second. Everything in calculus is all in terms of radians. Let's see if we got any more. That's it. Let me know if you got any questions. Good luck. Catch you later. Bye-bye.